Welcome. In this video, we are going to talk about reaction profiles. So we're going to be looking at the intersection between thermodynamics, which is looking at the energy of reactions, and kinetics, which is looking at reaction rates. And this will help us understand in a reaction mechanism why some steps occur slower than others, and also just in general, why some reactions occur slower than others, and what we might do to speed up a reaction. So our relevant objectives here, we're looking at topic 5.5, the collision model, and topic 5.6, reaction energy profiles. So in order for a reaction to occur, a reminder about our collision model for reacting is the reactants need to collide with each other. So here's an example showing the reaction between nitrogen monoxide and ozone. So they need to bump into each other in order for them to react and form products. And they need to collide with the correct orientation. So like if we want to form a bond between two oxygen atoms, we need to have those collide. Or in this case, we're going to have an oxygen collide with a nitrogen to form a bond there. So they need to collide with the right orientation in order to result in the right products there. And they also need to collide with sufficient energy. So these reactions involve breaking some bonds and forming some new bonds. They need to have sufficient energy to get those initial bonds broken and get that reaction going. So a key takeaway from this is that not all collisions will result in a reaction. So in order to react, the reactants need to actually bump into each other so they can come in physical contact and react. But not all of those collisions will result in a reaction. And we're going to focus in this set of notes here on the energy piece of it. So what do we mean when we say they need to collide with sufficient energy, and how does that energy affect the rate? So we're going to focus on the energy piece there. So we're going to take a look at these things called energy profiles, and these are diagrams that are used to show the change in energy throughout the course of a reaction. So your y-axis represents your potential energy, your x-axis represents your reaction progress. So you're just showing what happens during a reaction as you go from reactants to products. So notice this over here is the reactants on the left, products are on the right. We typically go from left to right here in our progress. And here's some more examples of these energy profiles. And what you'll notice with them is that they always go up first and then down. So the energy always increases initially before the reactants turn into products. There's always some kind of hill, some bump there in the middle. And that initial input of energy is known as the activation energy. That is the thing that is labeled E sub A on those two examples there. That's a shorthand for activation energy. So you can think of that as the energy needed to get the reaction started. And in order for a collision to result in a reaction, the energy of the collision needs to surpass the activation energy. So remember earlier on, we said that the collision needs to occur with enough energy. This is what we mean by enough. So the collision energy needs to be greater than the activation energy. So if you look over here on the left, here's an example where I have my reactant molecules collide, but they don't have quite enough energy to get all the way up and over here. So they're just going to fall back down here and stay as reactants. So it's kind of like imagine trying to push a boulder up a hill. And if you only get about halfway up and you run out of energy, the boulder is just going to fall back down here on this side of the hill. In this example on the right, shows what would look like if the collision energy is sufficient. So in this example, we've got your reactants that collide. They've got plenty of energy, so they're going to make it up and over this barrier. They're going to make it over the hill, and they're going to turn into products. So this over here is a successful collision, and we have formed the products in this reaction. An analogy, if this helps, also, we talked about like rolling a boulder up a hill. Another analogy you might think of is with like a net sport, like volleyball or maybe badminton or tennis. You need to hit the ball with sufficient energy to get it up and over the net. So if we hit it with enough energy to make it over the net, then we make it to the other side, and that represents we've got a reaction happening. Over here in this example, if we didn't hit it with enough energy, it's going to hit into that net and fall back on the other side. It's not going to make it over. So it's another example there. So let's think about how this might relate to rate and other variables that impact rate. So something we know from experience is that as temperature increases, the reaction rate will increase. And so we want to think about why this is. And so we're going to look at this graph, this Maxwell-Boltzmann distribution. I don't know if I'm going to spell this right. Boltzmann distribution. And what these graphs show, this is something that we saw when we looked at kinetic molecular theory of gases in Unit 3. But this shows the distribution of your particles at various energies. So like this blue line represents particles at some low temperature. The red line represents particles at some higher temperature. Notice as the temperature increases, this curve shifts over to the right and it spreads out here. And so now what we're doing is we're overlaying this new thing we're talking about, activation energy, on this graph. So let's say that we have a reaction profile over here. It looks like this, and it's got a certain activation energy. So if we were to kind of overlay this activation energy over here on this graph, then we could say, okay, this point right here represents the activation energy. Anything to the right of this dotted line has enough energy to react. So if the molecules are over here on the right, then when they collide, the collision energy is going to be greater than the activation energy. The molecules over here on the left, they don't have enough energy. So these molecules, their collision energy is too low. So these particles over here, when they collide, we will get no reaction. These particles over here on the right, if they collide, we will get a reaction. And so you notice what happens is when we increase the temperature of our sample, that would be like the red line right here, you see how we have a much greater fraction of your molecules have enough energy to surpass the activation energy. So like if you look at your blue sample, it looks like maybe only like 10% of your molecules are over here on the right, have enough energy. But in your red sample, maybe it's more like 30% of your molecules have enough energy to react. So that is going to make the reaction go faster, because if you have like 2 or 3 times as many collisions resulting in a reaction, that reaction is going to go a lot faster. So that's how this increasing temperature works. So it raises the kinetic energy of your particles, and you have a greater number of particles with enough energy to make it up and over that barrier. Another thing to think about with activation energy and how it relates to rate is that when you're comparing reactions, the reaction with the lowest activation energy will have the fastest rate. And this is assuming we are at the same temperature. So if everything else is the same, the one with the lowest activation energy will have the fastest rate. So here's a side-by-side here. And without knowing anything else about these reactions, I can say that this reaction is generally going to occur faster because its activation energy is lower. And the reason why here is we are lowering that activation energy barrier. So the result will be a greater number of molecules will have enough energy to surpass that barrier. Another way you can think of it is a greater percentage of those collisions will result in a reaction. So, okay, so let's summarize these relationships here. So we can see that rate and activation energy and temperature are all related. And if we think about a generic rate law, we know that rate is equal to some constant K times the concentrations of the reactants to some exponents. This is a generic rate law. So if the reaction, as the K value increases, the reaction rate will increase. And it turns out there's a relationship between the activation energy and temperature and your K value. And this here shows the mathematical relationship. You do not have to be able to use this equation. It is not on your equation sheet. So this is not something you have to apply mathematically. I just put that there for you as like an FYI. What you need to know is more the qualitative relationship, meaning what you need to know is that as you increase the temperature, that is going to increase the value of K, and that's going to make the reaction rate faster. And then if you increase the activation energy, that will lower the value of K and make the rate slower. So with temperature, you've got a direct relationship. With your activation energy, it's more of like an inverse relationship there. So some other information, we want to get comfortable with these energy diagrams. If we look in your notes here, and you can also always just hit pause to take a look at this slide here. We've got some labeled energy diagrams, and you can just see the various important points to be aware of. So this flat part at the beginning represents the energy of your reactants. The flat part at the end represents the energy of your products. This peak right here is the transition state. Sometimes we refer to it as the activated complex. That's at high energy point. The activation energy is the amount of energy it takes to go from the reactants to that high energy transition state. And then the heat of reaction is this difference here, going from the reactants to the products. We often use the symbol delta H for heat of reaction, or sometimes we use delta E. We use those in chemistry here interchangeably. And there we go. So let's talk about how this relates to like what's happening physically with like the breaking and forming of bonds. So we've got some energy input and some energy output. And you can think of that, that activation energy, the energy input, you can think of it as the energy required to break the bonds of those original reactants. So breaking things apart takes energy. And then energy will be released when we form those new bonds in the products. And depending on what bonds you're breaking and what bonds you're forming, it's going to change which of these numbers is bigger. So like in this example, the energy input is greater than the energy output. So it takes more energy to break these bonds than was released from forming new bonds. So we say overall this reaction is endothermic because there's more energy that went in than out. And if you look at the change in energy, the delta H here, we'd say it's positive. So there's a net increase in the energy. So energy is absorbed into the system. And that's what's going on there. Here's another example where, again, we always go up and then down, but in this case, the energy in is smaller than the energy out. So there's a net loss in energy. We'd say that the delta H for this reaction is negative, and we say that it is exothermic. So energy is being released overall. So there's a net release of energy. So the heat of reaction, again, we were just talking about this. We want to solidify this. It's the difference in energy as you go from the reactants to the products. And if there's a net increase in energy, which is what's shown here, delta H will be positive, and we call that endothermic. If there's a net decrease in energy, delta H will be negative, and we call that exothermic. And here's another side-by-side here showing an exothermic reaction versus an endothermic reaction. The sign of delta H is super important. When we're talking about energy, it's really important to think about if it's a positive or negative value. So was energy absorbed or was it released? So we just want to pay careful attention to sign when we get into our discussion of energy. All right, so here's, again, to summarize some of the main ideas here, is that your activation energy, it's like that barrier for a reaction to occur. In order for a reaction to occur, the collision energy needs to be greater than the activation energy. Okay, in order to speed up the reaction, we've got two options. We can increase the collision energy, give the reactants more energy. We do this by increasing the temperature. So if we increase the temperature, that is going to increase the kinetic energy of the particles, and it will increase the energy with which they collide. And that's going to make the reaction go faster because more of your collisions will be successful. So more of them will actually result in a reaction. Another thing we could do to make this reaction go faster is if we could somehow decrease the activation energy. And that is what adding a catalyst does. And we'll talk about catalysts in a different video. So thinking about these, here's a sample question just kind of looking at these Maxwell-Boltzmann diagrams. This is one from a 2013 exam here. And we just want to be comfortable with what these diagrams look like and what they're showing. So this one, it's the number of molecules versus the speed. Sometimes they represent speed, sometimes it's kinetic energy. And so you want to pay attention to that axis there. And what we want to be aware of with these Maxwell-Boltzmann diagrams is that as we increase the temperature, the curve is going to shift to the right and kind of flatten out there. And as we decrease the temperature, what we'll notice is the curve will kind of shift to the left and get a little taller and skinnier. The area under the curve will stay the same because you're going to have the same number of particles. We're just kind of changing what our distribution is, like how those particles are spread out at various speeds here. So in this example, the question is asking which of these graphs shows a speed distribution of the same sample at a lower temperature. So the correct answer for this one would be D. If you're looking for a higher temperature, we'd be looking at A. But this one, lower temperature, D would be the best answer. Okay, so just as a final reminder, as a consequence of these, thinking about these energy distributions here, the reason why increasing the temperature will make your reaction go faster is because at a higher temperature, you're going to have a greater portion of your sample will have enough energy to cause a reaction here. So I might go back and kind of like end with this slide here, thing that's key. So again, the activation energy is that barrier to a reaction. You can make a reaction go faster by giving your reactants more energy by increasing the temperature. And also, if a reaction has a lower activation energy, that will also allow that reaction to go faster. All right, thanks for watching.